should also read it, so.
You cannot read?
Well, I don't see all the indices.
You can't see the indices, or did I miss?
Not all of them.
You don't want to.
See,
Yes.
that's why I will have bigger trouble typing them out. Did I miss? What time is it? Okay. I'll try to decode this later. But really, this is not going to get so technical, so you can ignore it and just refer to a PDF.
Was machst du?
Okay.
Gefehlt, ja?
Wow. Yeah, okay. So, Bess was so kind to agree on telling us a little about magnetic fields.
Yeah, and I have more digits because I was at a conference, so I brought all this.
Yeah, so please. Thanks very much.
Used. Stefan asked me to talk something about magnetic field for electroweak phase transition. But actually, as you can see from my outline of the talk, this is going to be a brief talk on cosmic magnetism at large. So I'm going to touch and mention a lot of things, but not going to go deep into any particular one of them, except maybe the model that I'm currently working on. But hopefully, if you have questions, even if I'm not able to answer you, I will be able to point you to references of people who may be able to help you. So let's start from cosmic magnetism in large scale. I don't know how many of you would be interested in astrophysics, but I am. Magnetic field is observed in the cosmos, but the origin of cosmic magnetism remains an unsolved astrophysical problem. So astrophysicists have measured through elaborate efforts that magnetic fields are almost present in all galaxies of the strength of 10 to the -5 to 10 to -7 to 10 to -5 gauss over a large spatial scale, say of megaparsec. Some have smaller. They are also found in some galaxy clusters, and the observational techniques that are commonly used is synchrotron emission from free relativistic electrons, parity rotations. Those two are the most commonly used. And we can also probe magnetic field from distant objects through the spectral lines, Siemens splitting, as well as the optical polarization of starlight. But the puzzle for astrophysical magnetic field is they are observed to be coherent over large scales. Okay, so what are the proposed astrophysical sources? There's a mechanism called Harrison mechanism. Correct me if it's not 9070, because I couldn't find a reference in my laptop. It basically is very simple. It's just the differential rotational velocities of the electron-photon fluid and the positively charged proton would generate a current, and whenever you have current, you will have magnetic field. And also astrophysical objects can generate magnetic field just from the Biermann battery. I'm not sure if my pronunciation is correct, but basically it is resulted from the electric current resulting from different surfaces of constant pressure and density from rotating systems. And then both the source fields could then be much amplified by a mechanism called galactic dynamo to generate the large coherent field that we observe in galaxies. Yeah.
So which systems do you have in mind? The second point?
What do you mean by which systems? You mean which area when you have Harrison mechanism?
No, when you
I
see
think Harrison,
this Biermann one, when you say from rotating systems.
I mean, Biermann is fairly general, people, for example, apply this also to shock fronts. I would also classify this under Biermann battery effect. And so there's a paper by Koolsrud and others in about 14 years ago where they did such simulations, and that applied to a time of 10 to the 8 years. So it's late time in some sense. But it's I mean, one could even think maybe in some sense Harrison mechanism is a generalized or special form of a Biermann battery, one could also say,
Okay.
perhaps. But then Galactic was different. And that's much later, certainly.
Yeah, and I'm not an expert on galactic dynamo, so, but I'm just putting down some astrophysical possible sources. But one thing that has been noted in the literature is, and I'm not sure whether that's the reason why people then kept looking for cosmological sources, is vector perturbation is known to decrease with the expansion of the universe. But so you would expect to see sizable effects if you have these astrophysical sources at the radiation matter equality. But then this is incompatible with the current galaxy formation theory. That's what I got out from the literature. So, but anyway, we know that particle theorists are pretty creative. So, is it possible to help for this this cosmic magnetism mystery? Is it possible to generate cosmic magnetic field much earlier? So, that gets us to look at cosmic magnetism from small scales. So, there's a paper in 1983. I don't think he's the first one to propose that magnetic field could be primordial, but then I think this one is the first paper that look in detail the spectrum and the evolution of a primordial B field. The paper by Hogan. The first paper in terms of model building is the one in 1989. They look at the QCD phase transition because at that time, latest studies showed that QCD phase transition is first order. And then, so they frame the Biermann battery. Well, they propose certain kind of spontaneous charge separation in the bubble walls. And I hope I get this picture right. That they assume after baryogenesis in the QCD phase transition, you already have the excess of baryons in the bubble walls. And due to the difference in the equation of states of the quarks and the leptons, in the quasi-neutral plasma, we expect to have, or they wrote down that you will have electric field behind sharp fronts. And once you have this electric field, you would then generate a B field. But what's not very clear in this first paper is how you could amplify this C field from such a small length scale, because we're talking about QCD length scales, about 1 femtometers, I think. But the intriguing property of magnetic field is it's coherent over a very large scale. So subsequent papers, I think there were
What is the
4,
scale of
5.
QCD?
Is that 1 femtometers?
Yes, but it gets expanded by the expansion of the universe.
But I think they worked that out, yeah, by Hubble expansion and all that, and it doesn't match with observation because it's
Yes,
so tiny. And you also expect this.
Yes, it's
resonance.
tiny, but it's not. I mean, it's kilometers. It's not.
But we are talking about parsecs.
But what did you say was the scale?
What did I say about which scale?
That corresponds to QCD scale.
I said QCD length scale is 1 femtometers.
Femton.
Is that FM?
10 minus 15.
Yeah, that's certainly the relevant scale during the QCD phase
Is that
transition.
correct?
Yes, but then you
Yeah, then you stretch it afterwards.
stretch it, and then
Yes.
today that scale corresponds to kilometers. I mean, it's not such a small scale.
Yeah, but then we talked about parsec, which is.
Yes, but
I have to
look, I'm not referring to
Yeah.
that. What I'm referring to is the scale that you actually mentioned, femtometer.
Oh no, I'm just talking about all this microphysics scale. I'm not talking about the observed scale today. I'm not talking about fundamental scale. I'm talking about all these processes that happen at QCD level.
Yes, but then you should not compare it to parsecs.
Yeah, I missed out the important part, which is and then you have to evolve the field from all this microphysics scale back to today. But
I mean, she's basically
And this-
asking whether it could be relevant as a seed field. for the dynamo, because she was just explaining that the dynamo has a problem in having strong enough seed field to be successful for the galactic dynamo. So one is interested in strong seed fields, but and so one is interested in the scale of that magnetic field at a time that is now astrophysically relevant. And so she is projecting that, of course, to larger length scales. And I think, as you were saying, it would be kilometers, maybe even bigger,
Yeah.
Yes,
but smaller than 1 astronomical unit in any case. And so it's still much smaller than parsecs.
no, the point is just, yeah, for the they propose.
I understand all of this,
Yes.
but it's just that you should compare the
Yeah,
right
I
things.
saw the point, which is, yeah.
So the QCD phase transition, I thought that was at the time of 10 to the -6 seconds or 5 seconds.
Yeah, something like that.
No.
No, it's
And,
not.
and then,
And the size of the bubble is model dependent, and the size of bubbles today is there are no bubbles.
so the, but then the horizon scale would be more like 10 to the 5, 10 to the -5 centimeters, rather than -15. or 12,
Yes,
13.
that's the horizon
Yes.
scale.
No, it's much more than that.
The horizon scale?
Yes.
How come?
Well, multiply this by speed of light.
Yes, which is 10 to the 10 centimeters. And then 10 to the -5 times 10 to the 10 is 10 to the -5.
Not 10 to the 5.
Oh, 10 to the 5. Yes, that's bigger, of course, even that is bigger.
Yes.
Right.
Yes.
Yeah. 10 to the 5
But then the size of bubbles is also model dependent, and then you would end up with bubbles of the order of this size at the time of transition.
Yes.
Then you have to scale it.
Yes. But why?
Because
did you
I know
mention
that you have-
10 meters?
Yes, I don't know. I know that at the electric scale.
It's just something I remember QC the length scale is
At some point I calculated the size of bubbles at the electric
confusing.
scale, and it was 10 to -5 in horizon units. Now,
Yeah, I see.
at the QCD scale, the biggest it can be kilometers already at the QCD scale. But the size of the bubbles will not be horizon size.
Yeah.
It will be smaller.
Then maybe more.
So then you get to
centimeters,
centimeters or meters
Yes.
at the QCD scale.
Yeah, right, sure.
Sorry, it's confusing. My
No.
point in this slide is just to say that it's possible and people have proposed concrete models to achieve the same scenario. Okay, so quickly we then jump on to primordial magnetic field at the electroweak scale. Well, actually, it may just be half an hour. I didn't time it, so I don't know. So if you go to high energy scale, then we have the SU2 cross U1 hypermagnetic field broken to U1 electromagnetism. So one thing that's important if you have first order phase transition, as most of the people who are working on electroweak baryogenesis believe in, then something in the abstract space, the Higgs space, is actually important. I was sitting through a lot of discussion when you guys were talking about the collision, the reflection coefficient of the quarks and anti-quarks to get enough CP violation and all that. But so let's try to get something more abstract. Think about the abstract space of the Higgs field. The Kibble and Blanken in '95 showed for a toy model that in an abelian U1 model, when you have two bubbles collide, and the Higgs field try to equilibrate, and by certain geodesic rule, which is commonly used for topological field studies, topological defects in field theory, that they will produce real physical effects. Okay, and this is what all this is trying to relate to the phase of the Higgs field. And but the model that I'm working on is a little bit more physical, hopefully, if we believe in this non-perturbative object called the sphateron. So for people who are working on baryogenesis, sphateron is useful because it is the object that converts baryons to leptons that is responsible for achieving baryogenesis. Okay, that's not correct. Yeah, that's correct. Okay, but one thing that is important about sphateron is this characterized by this topological number called the Chern-Simons number, which would correspond to baryonic number change in baryogenesis. And here is a pretty picture for first order phase transition in baryogenesis in the electroweak scale. I think most people know this picture or have this picture in mind, but I'll just briefly go over it. So here we have the bubble wall, and inside we have the broken phase in which the Higgs gets the that, and outside is the massless phase, but then and the spiral transition is very active outside. So as the bubble walls move, no matter how fast they move, the spiral ones would then get trapped inside the bubbles. And so for baryogenesis, that's about it. But then for me, who's looking in magnetic field, we look more into, so what is a spheron? Well, if you look into the internal structure of a spheron, it is actually very rich. So people have found, refers to these two papers, if you want to look the details, that for non-zero Weinberg angle, spheron is an object with a large magnetic moment. Okay, so the schematic picture that people have come up with for the structure of a spheron is as such. You have, let me make sure I get this right. This is magnetic monopole, okay. This is magnetic anti-monopole, yes. Field lines coming out from magnetic monopole, and then field lines going into magnetic anti-monopole. So you have a pair of magnetic monopole and anti-monopole connected by a twisted string, the magnetic flux tube, okay. And so this may not tell us how it's possible, how it's responsible for converting baryons to leptons. But what's interesting is, for if you're interested in magnetic field, what goes for the magnetic moment when the spherons are trapped inside the bubbles. Well, spherons is just an intermediate step in this Chern-Simons number changing process. So any slight perturbation, we will expect it to cause the decay of the spherons. Okay, and inside the bubbles, okay, the conductivity of the plasma is very high. Okay, so we expect this magnetic flux tube, this magnetic field lines, essentially should get frozen. They're not going to go anywhere after the spheron decay. So could this be our magnetic shift field? Well, it seems to be a natural mechanism for the generation. But again, the very important key is this is all happening in the microphysics scale, very small. How can we sustain and amplify the field?
Let me ask you something.
Yes.
So you said that.
Hopefully I know more.
You said that this. Let's assume that this picture is correct, and
yes.
So you say that spherons, when they're generated, then magnetic fields will get frozen. But if the plasma, because conductivity is large, but if the plasma is so highly conductive, then why should it be generated in the first place? I mean, there is equal resistance to generation as to decay.
The resistance to generation of
magnetic field. This in the spheron, right? So what you seem to be saying, the way I see it, is that spherons which have with non-zero Weinberg angle, their generation should be hindered by the fact that they have this magnetic field.
Inside the bubble, spherons are damped, right? They're
I'm
only
talking about
active
symmetric
outside.
phase.
They're only outside. So I'm just talking about inside the broken phase, spherons transitions are strongly damped.
I'm not talking about that.
Yes. So what resistivity are you? I think I'm a little bit confused.
You said
yes
a few minutes ago that spherons have magnetic fields.
I have the
if there
internal
is
structures have
non-zero
this.
Weinberg angle, right?
Yes, you have this magnetic dipole moment, this flux.
And that because of high conductivity, that these magnetic fields will not decay. This is also what you said.
Plasma.
Yes.
Yes.
That's also what you said.
Yes.
Okay. So what I'm saying is that if they will not decay because of high conductivity, then also they will tend to be not created because of high conductivity.
But they are not created, they are just diffusing into the bubbles. I mean, if you believe in baryogenesis, then where do we get all these excess baryons? Inside the bubbles.
From spherons?
Yes.
What's this Faleron transition, though it's not a particle, yes, in this sense.
But
It's
she's
a-
here talking about particle.
Yeah, yeah, so it's a configuration, an
It's
unstable
the
configuration,
yes. It's the configuration
which
of
is
gauge
looking
field.
different outside and inside the bubble, yeah? I mean, the outside is a complicated object,
Yes.
inside is, it's...
Right outside the bubble walls, they are complicated going through.
Are you talking about
transitions.
outside bubble?
No, I'm just talking about the walls of spherons, just right outside the bubbles, they're undergoing transitions. But then as the bubble walls move, all this should diffuse into the bubbles. And so once inside the bubbles, this spheron's object should quickly decay. And then my argument is that because of the high conductivity of plasma, the field lines wouldn't just disappear.
Okay.
They would be there.
But my question is,
Yes.
if they cannot decay because of high conductivity, how can they be created because of high conductivity?
But what, the spheron or the magnetic field?
The magnetic fields that are required for the spheron.
Yeah, I mean,
What do you mean by magnetic field for?
You told us that.
The sphere, do you think the spherons would diffuse into the bubbles? Right?
No, I'm not talking about
he
diffusion.
is asking why there is a magnetic field in the spheron.
Well, if you have magnetic monopole and anti-monopole,
Then you have fields, of course.
then you have fields.
But if you have such a configuration in high conductivity plasma, then it's very difficult to create it.
But those spherons are, of course, coming from the outside, and there the conductivity was not high.
It is high,
Outside?
sure.
Outside the bubble?
Outside the bubbles is the plasma.
It's equally high.
But then you need
Yes, it's
rapid, well, my understanding of baryogenesis, correct me if I'm not correct, is you need rapid spheron transitions outside the bubbles for you to
Yes.
achieve.
And I'm asking, how come they are rapid if you require generation of magnetic fields of that time? That seems to me to hinder creation of fluxes, no?
Oh, you're talking about outside the bubbles.
Yes.
So Tomislav, your point is that suppose
But
you have
they
a
are all-
magnet. Sorry, if you have a magnetic, suppose you have generated a magnetic field outside, but this would prevent then more spherons from. You say there's a
I'm
negative
saying
back.
it-
There's a
it's
negative
not-
back reaction on the
No,
on the creation of
I'm
spherons.
saying
Is
this
that what
tolerant
you're
is a configuration that contains strong magnetic field in it, like monopole, anti-monopole, which is the picture that Bess is advocating, right? Then, if that is correct, then this tolerance should be suppressed. Once you take into account that they interact with the plasma.
I don't have the ideal answer for that, but I would think that they are confined fields. This is the internal structures. I mean, they're not like
Well,
magnetic fields.
it's an unstable configuration which
Yes.
has to be
Yes.
created, yes, to get this baryon, for example, baryon.
Yes, but this
Iodation.
configuration you're talking about lives in a high conductivity plasma.
Yeah.
And if you want to create this configuration, there will be resistance of plasma to it.
but that's
I think so are you saying that this general picture of the
I'm
structure-
doubting that
Yes,
this picture
yes, yeah,
that
I'm
this
saying-
picture is correct if you put this in the plasma environment. That's what I'm saying.
Oh, actually, that's something that I'm gonna mention later, which
Okay.
I thought maybe.
Okay,
Not
maybe
that
we
I
can
have an
put-
answer for that, but I'm just saying for people who are working in baryogenesis, I thought that's something that you want to look at.
Sure.
But sorry,
Yes.
I thought we know what the
spheron
spheron
and the
configurations
magnetic field
are
outside the bubble.
in the
Well,
standard
what I'm
model,
trying
for
to say,
instance.
has anybody simulated Spalaron transitions with non-zero Weinberg angle? That's my question.
Not simulated, but I think I have
Oh, really?
a reference for people who look into.
If this is correct, you might actually find out that they're suppressed. I don't know.
It's pure as you do.
Yes, it has been done in QSU too, but okay, please continue because this is.
No, we still have time. So, okay, so one thing that I was gonna mention is then, one thing that's, well, if you believe in that twisted flux tube picture that I showed, and then one thing that's interesting about that configuration of field lines is that the winding number is not 0. So, and then that would be something related to Professor Falkenberg's especially something with dynamo, helicity, astrophysical dynamo, people have found that when you have helical field, meaning linked field configuration, there's a competition between helicity conservation and energy conservation as the field evolves. Okay, and it is found in astrophysical context that actually helicity wins out. So there's a mechanism called inverse cascade in which the helical field is found to stretch from small to larger length scales. Is that correct statement? Okay, so that's something that they found in large astrophysical fields. So this is something that just makes the spiral magnetic field a little bit more interesting than the QCD phase transition, in the sense that if we have this helical field, twisted field, then if high conductivity conserve instead of dissipate out the SIP field, for then later on more complicated MHD studies would then tell us whether it's possible at all to sustain this field at all. Okay. So, well, this is something I was trying to learn for last couple of days because I wasn't looking into this aspect. But I think for people who are working in baryogenesis, they may be interested in this because you guys talk a lot about bubble wall velocities and all this quarks and anti-quarks. But I found one paper in which they done a study, not a numerical one. I think this is just an analytical calculation of what the magnetic dipole moment of a spheron. If I think they're just postulating there's a magnetic dipole moment, not postulating. They are not confining particular to the picture that I draw, but they're saying that there is a magnetic dipole moment for the spheron. And if there's a magnetic field outside the bubble wall, what's the effect of this on the transition and all this? I'm not sure whether that answered directly your question, but this is something that I found. So I think the conclusion is just that it lowers the energy barrier between the vacuum, but it does not have baryogenesis process. But one thing that's pointed out in a later paper is that since that people haven't looked into what the property of helicity of the hypermagnetic field, so we're just talking about the U1Y. Okay, this is not the U1EM. But if you have U1Y in this model, just the standard model, so if you have helical U1Y, what is that going to change anything in this electroweak baryogenesis picture? One thing that I want to point out is if we do have magnetic field or magnetic SIP field inside the bubbles, and then you guys also mentioned you have to look then into the complicated turbulence in the dynamics. Well, the magnetic turbulence should be important too, because the conductivity of the plasma is very high. So instead of just looking at kinetic turbulence, you may want to consider magnetic turbulence as well. So this is just a couple of things that I brought up myself, and it's nothing to do with Tammy, so if I make anything stupid mistake, it's not his responsibility, because he asked me to do all this on my own. So this is last slide, hopefully for some brief conclusions. So hopefully I've convinced you that it's possible, well, whether it's natural or not depends on your taste, to generate primordial magnetic field just from cosmological phase transition. But it requires a little bit hard work to amplify the length scales. And hopefully I've shown you that actually there's a lot of richness in the non-perturbative side of field theories, just from the spherons. Prove that. Understanding of the full bubble dynamics will definitely help for looking further into this magnetic SIP field generation. And also advances in MHD studies will have a lot. Right now we still don't know much about MHD. But one thing that's more exciting, instead of waiting till 2012 or 2016 for LISA, I don't remember the year.
Yeah, 2017 or something.
We actually
like that.
have a very upcoming probe for this cosmic magnetic field, which is the polarization data of Planck, which should be coming in a couple months. I was told that it's October-ish. So people have done elaborate calculations on what signals to expect, at what frequency scale, what peaks. And I want to, maybe the next slide. I'll give you 2 references, and also Tina is coming in late July, so if you have questions on that, you can ask her. Yes, and I think we should further an understanding of hypermagnetic field in the electroweak baryogenesis scenarios. So here are the references if you have further questions. So yes, for the last one, Tina has done, with her collaborators, have done some elaborate analytical calculations on what signals you should expect for cosmological magnetic fields from electroweak scale, both from CMB and also gravitational wave studies. And she told me she's coming in late July, so if you have any questions, feel free to ask her. And I hope the references will help. Okay.
So, thanks very much. Yeah, are there more questions?
Yes, I'm sorry, I don't really know how to think of the spheron. I was told that it's non-perturbative. It is the way you think of it, that if you calculate the...
Well, it's not non-perturbative, it's classical.
It is a non-perturbative solution of the field equations.
Oh yeah, you're right.
Right?
I mean, in the broken phase is classical, in the symmetric phase is non-perturbative, that's true.
So, and yeah, I took that
So what-
into faith, the
So what do
monopole
actually
and
James
monopole
and Hindmarsh say?
Hindmarsh.
Hindmarsh. What do they actually say?
They calculated, that's the, actually, did I put down the proper reference? That's the picture that they put in their paper.
Yeah,
one that actually-
but analytically, what do they say?
You mean the form for the magnetic moment? It actually depends on
The
which...
solution for the star, what do they say about it?
They took the one from, I think they just took the one from Manton, no?
Oh, but that's SU2,
And then
pure
the-
SU2.
No, it says you took us U1.
No, no.
I think, I remember they just took the one from Manton and then they picked a gauge
Oh, no.
and then they calculated.
Oh.
That's already the one with the
And then that's the one that but they have to pick a gauge.
So, but I was not aware that Manton solution breaks the axial symmetry. It does. Not axial, sorry, the spherical symmetry.
No, it doesn't, right?
Well, it does.
No, I don't know, I don't quite remember, I have to be honest, what they did because I looked at this paper a couple of months ago. And the final picture I have is this. But the Manton one doesn't break spherical symmetry. But
Right,
the,
right.
yes, I know. But the final picture that they draw out from the calculation is this one.
Maybe Manton Klinkhammer, I don't know. We can check. You know.
What is the energy of the spheron? And how was that generated?
How was what generated?
This
How was
one.
energy?
I mean,
How
what's
was
it? What's
How
it?
was spheron generated?
Yeah. I mean, did it emerge out of a previous equilibrium state at higher temperatures, or as a result of condensation?
I think what Manton found in the non-perturbative
Mhm.
solution for the equation is just the ground states of the standard model is not singular. So we have this topology of
Mhm.
vacuum.
I see. So it really goes back to all previous times.
Yes.
Uh-huh.
So it's just found in the model that
Yes.
if this is the field equation that describes the model, then
Yeah.
your solution is not just one ground state. You will have this degenerate
Uh-huh.
ground
But
state.
this
And
is
No,
the
but
no, this is not, spheron is not a ground state.
Yes,
This
but
is-
but spheron, I'm not finished. Correct me if I'm not correct. Spheron is not about the ground state, and I don't have the energy configuration. Spheron is the path in the what do you say that configuration
Yeah.
space for minimum transition between two different ground states. So
No,
whatever you
even
have
not
to-
that. I mean, that's just the unstable configuration on top, yeah?
on the
It's
So
an,
if
So
you
one
have-
has the infinite
Yeah.
many dimensional
yeah.
configuration space of fields, and you can actually find static solution, which is exact solution to the Higgs gauge equations,
Mm-hmm.
Heat-Young-Mills system of equations. That's what they've done, and basically, but that equation has it's not zero energy solution as it is the case with the vacuum,
Mm-hmm.
but it has non-zero energy, and at zero temperature, the energy of the order of 10, maybe even more TeV of that solution. That means, from the point of view of physics here in this room, it's completely irrelevant. However, from the point of view of physics at high temperatures, it's actually relevant because two things happen. First of all, if you have very high temperatures, the thermal fluctuations, well, this is actually the other point, as Michal pointed out, in configuration space, which means it might play a role in connecting two different vacuum.
Just like quantum tunneling.
Right,
Now we are tunneling
and
between
so
two
the
quantum
thermal
field
thermal
configurations.
fluctuation might take you over the barrier, but of course
But
the barrier is
it's not quantum tunneling in this case, it's
Yes.
thermal tunneling. Yes, you just
Mm-hmm.
Yes.
get over the...
now of course naively you would think, oh, I need to go all the way to few TeV to actually get a significant number of particles going over that barrier. But there is another effect, and the other effect is that the Higgs, the energy of the solenoid depends on the Higgs expectation value, and the Higgs at high temperatures shrinks.
Mm-hmm.
It actually gets thermal effect that reduces its expectation value, which reduces the energy of the solenoid, and eventually, at the critical temperature, the Higgs actually loses completely the expectation value, in which the solenoid barrier actually completely disappears.
Uh-huh. Mm-hmm.
So that means that the critical temperature, which is around 100 GeV,
Mm-hmm. Uh-huh.
this whole 10 TeV energy shrinks to zero.
So
Yeah.
these.
And solenoids become, and that means there is no more single configuration, well, single path in configuration space that brings you between the two vacuum, but this becomes highly degenerate path. So you need basically infinite many paths that connect different vacuum, and solenoids start behaving very differently, and they become, well, nobody has actually constructed it yet. But nobody
There's nothing analytical.
nobody
It's
has done any analytic
That's
work that would
lattice
actually,
calculation.
Mm-hmm.
that would actually, it is still an open problem. How do you actually say anything analytically about sphalerons? We still call them sphalerons, just for the language purpose, but they're strictly speaking not sphalerons. About those baryon violating configurations above 100 GeV.
Do they still contain Higgs fields or the pure gauge field configurations?
Both.
I still have both.
No Higgs fields.
Not in the classical
no,
solution.
In the also, yeah.
Yeah,
No,
sure.
not in the classical solution.
But it's not classical.
It's just in the
It's not classical.
determinants.
It's just quantum.
I think
Fluctuation.
strictly
Mhm.
speaking, sphalerone means you include the Higgs field. So I think at high temperatures you should talk about it as a thermal SU2 instanton, not a sphalerone. But that's language.
Yeah.
So these are pure gauge field configurations.
The classical solution is pure gauge field, and
Mm.
then you have to have the
Yeah,
quantum
yeah.
fluctuations.
Yeah.
But then fermions and Higgs fields are included on an equal footing.
Mm-hmm.
But the change in the topological number in the Higgs sector is matched by the change in the gauge sector. So you have these two equivalent descriptions, right?
You say topology in the Higgs sector.
Yeah, there's a relation between.
Yeah.
You can have Chern-Simons number, or you
Change.
can have Higgs.
Yeah.
Higgs
Higgs
winding
winding
number.
number.
Which
Yes.
are asymptotically related.
Yeah.
Asymptotically,
Yes.
they are not the same.
Yeah.
So maybe coming back to this magnetic fields, is this the only way of generating magnetic fields during the phase transition, you think? Or
In
does
electro
it,
wave.
yeah, so it have to be related to
I think
spherons?
there
or-
are both numerical and analytical studies in which people just look at the W plus, W minus,
Mhm.
bubble walls and all that. But essentially, I mean, my understanding is spheron consists of gauge fields. So that's, isn't that just part of this picture when you have, my understanding is the spheron decays and then I have all this plus and W plus and W minus. So I have this charge.
Well, these are
But
very
people
special
have done,
configurations.
explicit
so-
numerical simulations Well, actually, quant's work is not just electroweak, he's putting it at a much higher scale. But yeah, and then they evolve it semi-classically. But they are dealing specifically with the Higgs and the W plus, W minus, and they look at how the phase gradients and all that evolve.
In the Kepler-Vilenkin mechanism, right? They actually consider colliding bubbles, and
Yeah, and that's an analytical
right.
study.
And they basically say that somehow you can think of gradient of the Higgs field, if I remember correctly, that also corresponds to some direction of the field. And so you can assign to the bubble field direction, but that's not a covariant concept. But what is covariant concept is the actual, if you have two bubbles and they collide, the actual angle difference between them. And this angle difference in the Higgs sector will act as a source for generation of magnetic field. And that is a gauge invariant concept.
Here, when you want to put
And if you have, I
phase.
think, 2 or 3 bubbles, I forgot the details of the paper, but they've shown that if you have 2 or 3 bubbles colliding, that and that those Higgs angles should be random, and therefore there will be tension. There will always be gradients in this angle appearing as bubbles collide and come closer to each other and collide, and that will eventually source magnetic fields.
Which is a mechanism completely different from what Bess was
Yes,
talking
that's
now.
different. Yes.
That's the Higgs field gradient, so they put it into this language. Whenever you have a Higgs phase gradient, then you will have a source for the magnetic field.
Yeah, but it's in that equation.
In these papers, do they really show, I mean, how these magnetic fields freeze out? I mean, because normally you argue in the hot phase, well, you can produce these magnetic fields and also this follow-on configuration, which are important for baryon number violation. And then, if you go through the first order phase transition, yes, you come to the Higgs phase where these Sphaleron transitions are heavily suppressed. Yeah? So you would say there are, in your language, there are very few Sphalerons or better nothing, yes, because it would drive you back to equilibrium, yes, so
Yeah.
no baryon number
Same
anymore.
for
Yeah,
baryogenesis too.
yeah.
You don't
Yeah,
want
so
it to-
you try to kill it, but then you argue that if the Weinberg angle is unequal to 0, that there is some relict, yeah. So this is. In these papers, this really worked out, or how much?
I hope I get your question. You think this paper?
Yeah, in these papers, yeah.
Did they say, yeah, the whole calculation is done with non-zero Weinberg
Yeah, and
angle?
they really, but maybe did they really start from where did they start from? I mean, you should start from the hot phase, yes?
This is just, no, this is not done.
This is just in the
yeah,
Higgs
this is just
phase,
a
yes?
pure theoretical calculation of what is like
The
the structure of
this
Sphaleron.
dipole,
It
yeah.
doesn't involve all this phase
Yeah, but then one
transition.
could argue that, I mean, these Sphalerons in the Higgs phase should be heavily suppressed, yeah? Exponentially suppressed.
You're talking about the broken phase?
It's a broken phase, yes, in the Higgs phase, yes?
Yeah, but these are, I think, broken phase Sphalerons.
Yeah, but then they are still, you say they are still there, yeah? In a sense, yeah.
I mean, they're suppressed by simply Boltzmann suppressed.
Yeah, they're heavily Boltzmann
Yeah, if
suppressed.
you like, but that is from suppression, yes?
Yes, it is.
Yes,
For a
yes.
strong phase transition, the rate is less than 100 times.
Yeah.
That's what is defining strong.
Mhm.
There is also a Dutch physicist, Pierre van Baal,
Mm.
and he has actually, I think, constructed similar type of configuration, but of course they're not Sphalerons. They have sort of two monopoles
Mhm.
connected.
But on a torus, I guess. He
Sorry?
likes stuff on a torus.
I don't quite remember what precisely it was, but
I think he tried to do this stuff on topologically non-trivial manifolds.
he's done a lot of work on things like that.
Mm.
Does anybody know about the when one talks about CMB, so the electroweak phase transition would correspond to a CMB scale which is at very high multipoles, beyond what one can observe, doesn't it?
Much higher than
Much higher L.
If you just the scale of colliding bubble, an electroweak scale, if you just scale it,
Or even horizon.
Yes, you would not be able. If you just scale it naively with the expansion of the universe, you would not be able to see it in
A
CMB.
few 10,000 or 100,000 of L.
You would also not be able to see the even QCD transition. However, the hope is that if you include this inverse cascade or turbulence, that will further stretch the scale a little bit.
Okay.
And then even that is questionable, whether you'll be able to observe it on small scales in CMB. But I think you should be able to stretch it enough for the scales of galactic dynamo. Maybe. It's not well established as far as I know.
I think what the CMB studies usually do is they could put a constraint on what's the
On
strain.
fields of larger scale.
Yes.
Yeah. So, but it wouldn't be, if you don't see it in the CMB, it doesn't mean that it may not have a rise at the electroweak phase transition.
Yeah, but I should look at one of the papers that I brought and say
Well,
what
you
is
have
that.
activities in the fields,